we talked about the de Broglie equation earlier, and what that said was that all matter has both wave properties and particle properties. The smaller the matter is and the faster it's moving, the more its wave properties are going to affect its behavior. The bigger and slower it's moving, the less the wave properties affect its behavior. So there was probably one video where we talked about the de Broglie equation that may have went over your head a little bit, and that's okay. The de Broglie equation is not on the exam. But you do have to understand what it says, I guess, like the conclusions drawn from it, and that's that smaller, faster moving particles have wave properties that do affect their behavior. So the electron essentially acts as both a wave and a particle all the time. Okay? So it has wave-particle duality. That's what we say. Where this came from, we had this guy, Niels Bohr and Erwin Schrödinger. They're both famous scientists. Bohr was looking at the atom where the electron acts as a particle. Schrödinger's looking at it where it acts as a wave. Turns out it acts as both. And I don't want to bore you with the history too much. I don't think that this diagram does a great job illustrating the waves that I want to talk about here. But because the electron acts as a wave, okay, the electron must be bound to wave properties to some extent. And I don't want you to start thinking electron or atoms look like this, but this is good for modeling. So atoms, first of all, electrons do not travel in predisposed paths like this. They don't travel in orbits. They travel in orbitals, which we'll learn about later, and that's really not traveling in any defined path. They have probabilities where you can find an electron. But this is good for modeling cases. So the electron, remember, has both particle and wave properties. So it's going to act as a wave, and here we see it acting as a wave, right? So it's moving in this wave pattern right here. Waves are suspect to interference, either constructive or destructive interference. So if we look, here's an example. Well, I just went back on the page. Here's an example of constructive interference, right? So these two waves, if you add them together, you get constructive interference. Okay, here's an example of destructive interference. So if these waves are out of sync and you add them, if they're completely out of sync, they will destructively interfere and you'll have no kind of wave at all, right? And this actually, in a roundabout way, explains why you don't find electrons in the spaces, really, or why the probability of finding, I kind of hit the top of the screen there, why the probability of finding an electron in the spaces between energy levels is limited. So why is the probability of finding the electrons much greater in this space and this space than it is in between here? And it's because of this destructive interference that happens, okay? So if you take the principal energy level, or kind of the distance out from the nucleus, and you try to assign a fraction to it, you get this mismatch that occurs right here. And this mismatch leads to destructive interference, okay? And all of that wave property duality kind of goes to explain this phenomena that happens in chemistry. You might have asked yourself, why are electrons always pictured as being in these spaces? And remember, this is a very simplified version. They're actually, it's a probability of finding them, but why are they much more likely to be found here and here than in between? And it's because of this destructive interference. So this is called the wave mechanical view of the atom, and I think this box does a great job of talking about what's going on. So the hydrogen electron is visualized as a standing wave around the nucleus. Okay, so here's our standing wave. The circumference of a particular circular orbit would have to correspond to whole number wavelengths, as seen as n equals 4 and n equals 5, or else destructive interference occurs. This is consistent with the fact that only certain electron energies are allowed and the atom is quantized. Okay, now this is not the most modern view of the atom. The electrons do not travel in these predisposed little waves, but this does account for why we don't find electrons in between. When we move forward in the next couple of videos, we will continue to refine our view of the atom. But I do hope that this explains why electrons are not found why the probability is very low at finding electrons kind of in these spaces. I'll see you in the next video.